And this is the last class with some new material, since next class we're going to do some review. And let's see if we can get through everything. I hope so. First of all, I want to go over again something we were discussing in the end of last class, just to make sure that you understand the whole picture here. We were discussing the flow around the sphere. And we said at very low Reynolds numbers, this section over here, we have Stokes flow. And so the coefficient of drag depends, it has an inverse relationship with the Reynolds number. It changes as 24, the CD here is equal to 24 over Reynolds, and this is the result due to Stokes that we also called creeping flow some time ago. And this agrees with experiments. As you can see here, all of the little balls in this picture are actually experimental results, and so the experiments agree very well up to about a Reynolds of 1. You see? Then the actual experimental results sort of diverge away from the Stokes result, and in fact they continue to, the CD continues to decrease, but more slowly than it would following Stokes' law, as seen over here. What is happening here is that there is some separation behind the sphere. And I have found here one experimental result which corresponds to Reynolds 118, so more or less around here in this plot, so in the middle of this range where we have this separation, the wake in the back. So what is happening between, in this range, all the way down here, is that the separation point behind the sphere, not very round, but there's a separation point, okay, more or less here. This separation point is moving forward. There's a recirculation zone like that, as you can see in the experimental results. And then as we move down this curve, the separation point moves forward until it reaches more or less 90 degrees like this, which is what you see in this picture. This picture here, you see? Once it reaches the 90% and the separation is right at the maximum, that level of, level of maximum area exposed to the flow, then it stays that way. It can't really move any further forward because that's the point of maximum exposed area to the flow. So because the point of separation remains there for a while, you see this behavior, which is that the coefficient of drag basically doesn't change. This is another region over here. I've found this, this is, I think, the Reynolds number in this case. I didn't write it down, but it's about 10 to the 4, something around 10 to the 4, I think. From where I put the arrow, maybe 1.5, 10 to the 4. I forgot to write it down, the number. But that's about what it is here. So you see the point of separation is right there at the 90-degree angle. And it remains there with this area in the back. This wake area in the back, separated areas like a sort of like a cavity in the flow, if you will. And so there's reduced pressure there, and because of the difference in pressure, we have less pressure in the back than in the front. This is the source of pressure drag. There's a difference of pressure between the back side and the front side, and this remains more or less constant all through this point around here. Now what happens in this area here, this is what is called the drag crisis, or some people call it the drag crisis. And what happens here, I was saying at the end of last class, is that the boundary layer, which is that very thin boundary layer that you see in this picture, you can't even see it, right? It's a very thin boundary layer for this high Reynolds number, becomes turbulent. When it transitions to turbulence, the boundary layer, if you recall, on the flat plate discussion, we had boundary layer is very, attached, and then the turbulent boundary layer is characterized by a lot of eddies of all sizes. These eddies in the turbulent boundary layer contribute to the transfer of momentum. So there's an increased momentum flux in the turbulent boundary layer. And this increased momentum transfer means that the faster fluid that's around, outside the boundary layer gets caught in. So there's more of this faster fluid getting close to the surface, and that has the effect of moving the separation point again to the back a little bit. And so in this area here, what we have in this area here is that again we have the separation point moving to the back a little bit. We have a very turbulent wake, but the separation point is not at the 90 degrees but further back. So separation is delayed. This effect of delayed separation means that there's now a reduced effect of pressure drag, and this is called the drag rise. The CD falls sharply there. This is a very, very interesting result, a very interesting observation that because of the reduced size of the wake, we have a net pressure force in the sphere which is reduced, and the drag coefficient decreases. So a turbulent boundary layer, because it has more momentum flux than the laminar boundary layer, resists the adverse pressure gradient better. Remember, we discussed adverse and favorable pressure gradient. There's favorable pressure gradient in the front of the sphere, adverse pressure gradient in the back. A turbulent boundary layer is better able to basically climb the adverse pressure gradient. This is, of course, a very interesting effect for sports. All sports that use a ball are affected by this. And in fact, so let me just say that the drag coefficient here falls by about 1/5 between the laminar and turbulent case. So not by 1/5, to 1/5, so it's 5 times smaller. And the reduction of drag can, of course, affect the range of a ball in sports. So if there's reduced drag, the ball will be able to travel a greater distance, which is important for many sports. So, in fact, I found some very interesting articles about the effect of the drag crisis in sports, and I've put some articles on Blackboard for you if you're interested to enjoy this discussion. I found some actual numbers. If you consider a smooth sphere, like a ping pong ball, the critical Reynolds number in the case of a smooth sphere, the transition between the laminar and turbulent boundary layer, and thus the occurrence of the drag crisis, is at a Reynolds number of about 4 times 10 to the 5. So 400,000. If you add some roughness to the sphere, for example, a golf ball, then the roughness has the effect of what we call tripping the boundary layer. That is, producing the transition to turbulence at a lower Reynolds number. And so in this case, golf ball, for example, the Reynolds number, the Reynolds number is 10 times smaller. You see? 10 times smaller. And so it happens that a golf ball, in the regime of the sport itself, is at that is actually past that transition point, so that it's made to have, by its roughness that is created by the dimples, is forced to be on the turbulent regime when it's at play. Well, of course, in the fast moments of the game. So, like I say, I put some very interesting papers I found on that you may want to browse just out of your interest. There's a paper there about the aerodynamics of baseball. Of course, the seams of the balls have that effect as well of creating turbulence. And there's some other effects of spin, which we'll discuss a little later. Yes, ma'am.
Does that mean that if the were the same weight but it were smooth, it wouldn't feel as hard?
Yeah, exactly. That's exactly what it means. If the ball, well, depends also in the strength of the player, how hard the ball is hit, and what the velocity is.
It's the exact same case, but with the dimples and with it smooth.
At a certain velocity, right, at a given velocity, if it's right there at the transition point, the smooth ball, it might actually not be in this region. It might be a little bit over here. But once you add the dimples, you make basically what you do is you make this area of the curve move backwards so that it would experience that drag crisis at a smaller Reynolds number. So at the velocity that you hit the ball, it will always be turbulent, and it will have this reduced drag, and it'll have a greater range. That's the effect of the dimples. Yeah. And in fact, because of the great economic incentive to develop better balls over the years and years, right? There's been a lot of research in this topic. Right. Okay. So you notice that this is a bluff body that experiences separation. In an airfoil, most of the drag is actually due to friction drag, not pressure drag. And so this is what we're doing here is delayed separation. In an airfoil, you don't even want separation, right? Because the airfoil may stall. But there are indeed other, I think, for example, there's some aquatic devices that have some, I don't know if you've seen the humpbacks have some roughness in the fins, and there's some also hypotheses that that produces a similar effect, and so there have been some devices that have imitated that geometry, but of course there's plenty of research in this area, but it has to be a situation where you have the possibility of having this effect of delaying the separation. But if you're perfectly streamlined airfoil and you don't have separation at all, then you don't want to increase the friction drag, because of course dimples will increase the friction drag, but they will reduce the pressure drag. And so pressure drag has to be dominating. At this point, let me see, I had the number right here. Let me see. The friction drag, yes. Because the dimples, you know, you have simply increased... So you're taking away from No. Remember, you might remember that when we discussed the actual boundary layer on a flat plate, we said that when you go to turbulent, there's increased wall shear. The wall shear increases because of the effect of the dimples, right? Okay. What is happening in this case is that, let me see, for a Reynolds of about 1,000, so around here, about 95% of the total drag is pressure drag. Okay? So the effect is mostly due to the difference in pressure between the back of the sphere and the front of the sphere. This is true for all bluff bodies. But the situation for streamlined bodies is quite different. You have most of the drag caused by just wall shear, friction, not pressure drag, not the wake. This is the effect of mostly the wake. And so the drag crisis is having an effect only on this part. And this happens in all ball sports and ballistics, artillery, if it's going, of course, we haven't brought in at all any discussion about going, near the speed of sound. So this is all discussion that has to do with only incompressible effects. But if we're not talking about supersonic ballistics, if we're just talking about the old-fashioned, 19th century artillery sort of thing, then you see all these effects. So again, if you're interested, I do invite you to look at some of the papers that I've put for you on Blackboard, because actually they're very interesting, some of them. There's discussions of about soccer, the latest ball. There was a lot of articles about the latest ball, the ball for the 2010 World Cup. There was a lot of studies about the aerodynamics of it, whether it was right, if it was operating, depending on the roughness and the characteristics of the ball, if at the speed that the athletes strike it, it is right here, then the behavior could be a little bit erratic, because it could be just at, just at this point where a little bit difference in speed makes a very big change in its behavior. And then for a while, people were complaining that the ball had some erratic behavior and so on, right? And so there's tons of papers published. People went and put the soccer ball in the wind tunnel and studied and published a lot of papers on that. So I found baseball results, soccer results, and tennis results there for you. And even some cricket. Of course, you can Google all of this, but I've collected some of the best papers and I've put them for you immediately so that you can find them. Some of them are already up there. Some of them I've got in my hard drive, and I need to put them still in. Okay, so moving on. Here is actually a very, very clear picture of what's going on. This is a bowling ball that has been thrown into a pool of water. In this case, the boundary layer is laminar, and you can see that the separation point is right at the 90 degree location, and this other one is going faster, and it's going at the same speed, but it says that there's turbulent flow induced by a patch of sand on the front. So they've created a turbulent boundary layer by roughness in this case, and that has delayed the point of separation, and that makes the wake smaller and reduces the pressure drag. So similarly, the flow around a cylinder also experiences a drag crisis, but the experimental results are a little bit different. But also the drag coefficient varies sort of as 1 over R, proportional to 1 over Reynolds in the creeping flow regime. Then around Reynolds equals 10. There is separation in the case of the cylinder. Separation, and you will see the similar pattern experimentally with these recirculation areas in the back. My picture's not very good, but you get the idea. I think I have some actual photographs in a moment I'll show you. And then what happens at a Reynolds number of about 90 is that this sort of symmetrical wake that is behind the cylinder actually starts shedding from the cylinder, and you get this eddy that we have here. Let me make that drawing a little better so that it actually makes sense. So what we have here is a separated wake with a recirculating zone like that. Okay, so two recirculating zones, like little vortices there, two little eddies in the back that are just, swirling around. The fluid is swirling around. At a particular point, the swirling flow just gets too strong and it sheds, so that you have this. It just goes to the back, and you get an alternating shedding of these vortices. These vortices that are shed from the back of the cylinder produce an oscillating force on the cylinder itself. These oscillating forces can actually, it's like a cyclic pressure on the cylinder, okay? This periodic force can sometimes produce things like, for example, the singing of the power cables, the flapping of the, the rope on a flagpole. The antenna of the, very good. The antenna in the car, exactly, yes. So let me show you some pictures. Here is close to the creeping flow situation where we don't see almost any separations. These are actual experiments. This here, Reynolds 26, we have in the back the two recirculation. It's kind of like a recirculation bubble, but it's just stuck there in the back, okay? But then at one point, for high Reynolds number, this recirculation bubble sheds out like vortices that are now dragged in the wake of the cylinder and can produce these oscillating pressures. Now, this is a phenomenon that was observed and described for the first time by a very famous fluid dynamicist called Theodor von Karman. Theodor von Karman studied the flow of a cylinder, and in 1911 he published some material, some papers, where he recognized this phenomenon of vortex shedding. Now, he points out in his writing, and this, you recall that I talked to you about this little book in Dover edition, Aerodynamics, which is more like a historical description of aerodynamics, and I've put the link on Blackboard to the book on Google Books, where you can read most of it. It sounds so very cheap, I think like $14 or something, if you're interested. But you can read it mostly on Google Books. And there's an area, there's a place where he talks about this. He said that he had seen a painting in a museum in Italy, much before his publications, where a painting which depicted the Saint Christopher, and with his feet ankle high in water, and the painting clearly shows this row of alternating vortices. So here's another one now, a more drastic representation of the von Karman vortex street, called now, like I said, in 1911, published by Theodor von Karman. And I found yesterday the actual painting that he refers to in his writings, and here it is. This is an article that appeared in Nature, the year 2000, just telling the story about this picture. It's a damaged picture, not completely preserved, of some saint, and this clear depiction of the vortices. And apparently Theodor von Karman said that this inspired him a little bit to look at this phenomenon, and he explained this in his autobiographical writings. Now, vortex shedding also excites oscillation. Oh, I have another couple of very, very good pictures. Okay, watch this. The vortex street is called because, I think it is because the actual, you see the alternating pattern here is kind of the same alternating pattern that you have on the street lightings. So in the past you had the lights in the streets were like this. So this we're talking about the beginning of the 20th century. So. And look at this one. This is an image from a satellite. What you see here is there's a small island, and the cloud cover is just at the exact height that it is, the clouds are visualizing the effect of the von Karman vortex street produced by the wind going behind this island. There are many photographs like these nowadays actually in the NASA sites from satellite observations, and here is another one. I think this is very amazing. Here is a really amazing one from the, this is the Juan Fernandez Islands, known as Robinson Crusoe in Chile, or further, and this was taken in 1999. An amazing photograph where you see very clearly the vortex shedding behind this island. The island is down here at the bottom, yep, and the wind is in that direction, and here are the vortices visualized very clearly by the cloud cover. Cool, huh? I think that's very cool, actually. The island is the bluff body. The wind is just going around it. There's vortex shedding around this bluff body, and the clouds are just at the exact right altitude that they visualize this effect. And this is captured by the satellites. But the final thing is that this shedding, of course, excites oscillations, and in certain structures, if these oscillations are anywhere close to the natural frequencies of the structure, then you can have resonance effect. And that resonance is what caused the collapse of this bridge. And I want you to see this. Let's take a little bit moment. I don't know if you've all seen it, but just watch. This is a video from 1940. So I'll just let you watch this one. I think there's some very peaceful pictures in the beginning of the building of the bridge. Who has not seen this? Okay, about half the class. Inauguration of the Great Bridge. A few days later. Now watch, please keep an eye on here because there's a guy running in the middle that appears at some point.
The only casualty was the dog.
All the details are in the Wikipedia article, and I've put the link on Blackboard for you to read. Here's the guy running in the middle. You see him? You see the guy running in the middle? Just barely? Trying to... Now look at the other section. The other section started moving as well. People didn't actually know this very well at the time. The phenomenon was not really very well. Nowadays, of course, this is a serious matter of. Now you're starting to see some failure. Look at that! Look at the amazing deflections there. That's concrete.
Oh, no.
That's iron. Steel structure with concrete. And look at that. Yeah.
And they just kind of kept focusing their Oh, yeah.
Sorry? Oh. There's a new bridge, yeah. Oh, okay. Well, here this is vortex shedding. This is a purely aerodynamic. The effect is vortex-induced vibration. The vortex shedding, as I've from this cartoon that I've found somewhere, can cause different sort of oscillations depending on how the vortices are shed. You can have forces in this direction, in the direction parallel, oscillating forces in the direction parallel to the wind or perpendicular to the wind, which apparently also is one of the things that happened here. So, as you can see, very important aerodynamic phenomenon. And to avoid such vortex-induced vibrations, some cylinders nowadays are constructed with some fins. For example, here you see a tower with some deflectors, in this case helical deflectors or fins. There's some other sorts that are used to destroy the symmetry of the vortex shedding, and because of that, they can actually build them with less materials, and because they don't have to withstand this. The effect of vortex shedding is less pronounced, and they don't have to strengthen the structure so much. So this is nowadays one of the ways that this is being dealt with. Yes.
So, is it like the Chicago fire?
No. No, but there's also There's also the case of this huge, the tallest building in the world, the one in Saudi Arabia, Dubai, yeah. That also is built in a way that all of the different floors have, they're asymmetric. So there's they purposely introduce asymmetry on the construction to reduce the effects of the shedding of vortices, because it would be very pronounced at those altitudes. Yeah. All right, so I guess this is now time to take a break, and we'll discuss force of lift when we come back.